I'm Anthony Scodary, co-founder of Gridspace. This class only happens every couple of years, and the last couple of times we've talked about end-to-end neural speech synthesis, but I'm actually pretty excited. Obviously, things are going really fast in the field right now, and so today we're going to talk about actually the engineering challenges of building a spoken dialogue system that leverages language models. And so really quick about me and about Gridspace. I'm Anthony. My background actually was originally at Stanford, was physics and then aerospace. And I was at NASA Jet Propulsion Laboratory for a long time doing scientific instrument signal processing and building scientific instruments. I worked on like the Mars Curiosity rover. I worked on the Juno mission to Jupiter. But my background was actually using high dimensional signals to drive robotic autonomy, which is what got me into deep learning, and then eventually I got interested in speech, and this was over 10 years ago. And my co-founders, Evan and Nico and I, are all friends from Stanford. About Gridspace, we are focused on being a center of excellence for language and speech technology, right? So we build ASR, speech synthesis, we build large language models, dialogue systems, we build everything. Everything you've been learning about in this class is kind of what we do. But here, in general, what we focus on are interactive systems, long-form systems, so not a voice assistant, not like Alexa, but things where it's like 10, 20-minute long conversations where people interrupt each other, rely on context for meaning. Everything's conversational, everything's speech. We operate on signals, not on just text. And then we build applications. We don't build APIs. We build a system where a relatively non-technical user base can build spoken dialogue systems and can build analytics. So what we're going to talk about today, I'm going to do a little bit of motivation, and then we're going to talk about the overall engineering challenges of building a modern spoken dialogue system. And then we're going to go through 4 key engineering areas that you need to do to make these systems practical and applied. And then we'll do a quick demo and questions, and we can talk after if you guys are interested in learning more. So motivation. So the laser was invented in the 1960s. It was one of those sorts of scientific discoveries where it had been postulated earlier on, actually like by Einstein, that you could build a laser. And when they built the first laser, everyone recognized the significance of it and the power of the technology. But actually, many of the applications that really ended up being a big deal that came out of lasers required another 20 or 30 years of refinement, like telecommunications and all these other applications of lasers, and obviously refinement of lasers from like big Heaney lasers like this one to diode lasers. And in general, the problems that were downstream of building that raw technology, the refinement, the engineering problems were very hard, very technical, and took a lot of people working on it for a long time. Similarly, in general, obviously language models aren't new. There's been statistical language models since the 70s or longer. But as we have learned how to scale up machine learning models to larger corpora, to larger hardware, and obviously with like models like transformers that allow you to better scale up your models, we're building systems that are obviously very impressive and have a lot of raw power, but are not really well constructed for refinement and for application by themselves, except for in certain niche use cases. And so the problem is we want a person to be able to solve a complex problem using a machine on the phone, right? And so we need a dialogue system, obviously. It needs to be spoken, it needs to be task-oriented, it can't just be like a frame-based system. And it needs to leverage large language models, right? We want to be able to have the best NLG for improvisation, for question answering, and we want to have state-of-the-art NLU for form filling and slot filling and stuff like that. So what are the problems we run into when we try to do that? Well, here, this is like a diagram, a cartoon I show a lot, of the full loop, right? And so we have, we start with ASR, and then a dialogue system and speech synthesis, and then it goes through the internet and through the phone networks, and then eventually sound waves and the cochlea, the brain, all the way back through a microphone, back through phones, and then back to ASR, right? This is the loop that we have to engineer against versus like analyzing text. These all have neural networks, these all have physical effects, these are all noisy, these all have distortion, these are all lossy, and all of them consume latency budget, which is really important because this is an interactive application that has to feel like a person on the phone. And so those are the core problems. Specifically for spoken dialogue systems, and this is not new, we have to deal with noise. We have to deal with non-grammatical speech that doesn't transcribe perfectly, even if transcribed perfectly with 0-word error rate. We're very latency constrained. And then we have turn-taking, interruptions, all these problems that generally don't occur in most written dialogue systems. And then task-oriented dialogue systems, traditionally, something like Dialogflow or an older task-oriented dialogue system, they're very burdensome to offer, right? You're building these very large state trees. It's very hard for even a conversation designer specialist, much less like a layperson, to build one of these systems. You have extremely rigid NLG, like generally you just have script responses and triggers. And the NLU typically struggles to use things like context and uncertainty. So that leads us to our four main themes for engineering optimization, right? One is control. The second one is minimizing latency. The third is making the system feel more natural. And the fourth is making the system robust so that we can actually deploy this. We deploy our dialogue system Grace in hospitals, in like largely scaled up insurance companies and financial service companies. These are real use cases where you can't just have someone open loop in a language model like ChatGPT. It has to be a system that's reliable and is actually enterprise grade. So we'll start with control. This is the cartoon from Drowsky and Martin. Basically, any traditional spoken dialogue system might look like this, similar to kind of the cartoon I showed, where there's ASR, you have NLU, you have dialogue state tracking, you have your dialogue policy, you have NLG, and you have your TTS. What I want to talk about is how you basically extend this model to leverage language models, at least in our case, how we've been able to do it. So this is a sub-piece of the dialogue, or the diagram I'm going to show in a minute. The main loop is that you have two systems interacting with each other. Some sort of language system. This could be a person. This could be a document base or a knowledge base. This could be a few shot examples for coaching. This could be other systems you'll see in a minute. Anything that operates in natural language. On the other side, you have the core dialogue policy, which is, the goal is to leverage our language models as much as possible to simplify our dialogue policy. So a traditional dialogue policy and dialogue state tracker might be extremely complex and highly authored. The goal is to instead leverage these language models to act as basically transducers going to and from the language system that they regulate. And so we're going to reuse this pattern. So in this case, I've suppressed having two language models for each of these systems. I know this is kind of a confusing diagram, but the idea is you have the caller over here, that this is the person speaking to the machine, and there's a language model going both directions that are highly specialized to language understanding, language generation, dealing with the caller. This is probably the part that you think about the most. But with regards to control, there's other language systems that generally impact what you might see in an enterprise or a call center or any business that has a large amount of, that needs to be able to control these systems. So we have something called like playbook, which is basically where the definitions for what the business process forms, what the bot is allowed to do. This is essentially a website that's highly specialized for its own language models that is authored so that you can control what the bot's allowed to do. It's inspired by what humans use for scripted call centers. Similarly, you have episodic few shot coaching. This is what we call just agent coaching, which is inspired by how you might, through role play, correct individual behaviors that the bot does. And then we have some sort of RAG system down here that we call knowledge base. And these are all inspired by real systems used by human call centers. And most notably, there's 8 language models that are all fine-tuned or specialized or trained from scratch to do these subtasks and to be regulated by one dialogue policy that basically treats them as different sub-applications. And so the key things you can see is DST has been offloaded more and more onto external software systems. So rather than tracking dialogue entirely in one system, you've offloaded it to subcomponents that are ordinary software systems and language systems. You also are relying on the dialogue history to do some of the dialogue state tracking as well, if you have a context window large enough in your LLM. NLG is pretty restricted based on upstream data systems. So all these systems are suggesting things that could be said based on what data they have access to. So the knowledge retrieval system, or the RAG system, is suggesting dialogue based on documents. The few-shot coaching is suggesting what to say based on past interactions. And the playbook system is suggesting scripted dialogue or behaviors that was authored. So the LLMs are acting more as an interpreter rather than a single monolith. So as opposed to something like ChatGPT, where you're just in the loop with language model decoding, here there's a large number of language models that are working together. The idea is that we want to reduce variance, have more specialized systems that don't need to be as large in some cases. So smaller models, less fine-tuning. It allows us to restrict interfaces in a way so that we can make our dialogue policy simpler. And it allows us to encourage truthfulness because we are generating across multiple steps. and then slowly coming to a conclusion about what we're able to say. The next step is, so fusioning of authoring tools and models. So like I said, we take inspiration from human software. These are basically simplified software tools that could be used by a person, a search engine, a little website. And this leverages the author's previous experience building these systems for humans. The knowledge base is a RAG system, and as actually is the coaching system. And so it needs to be able to retrieve quick enough that it can be done real time. It needs to leverage LLMs for pre-processing. And in general, you can leverage fancier search systems, but in general for us, a lot of times the document sets are fairly small, even for like a large call center, at most maybe 20,000 documents. And then breadcrumbs and source citations. So the idea is that the dialogue system has to leave a history of why I was able to make a certain decision for a dialogue suggestion, and then there should be a traceability from what document was suggested or what coaching session was used to make a decision about dialogue. Same with playbooks and task orientation. This is what makes it a task-oriented dialogue system. This is where you can do routing and form filling. So we're trying to really reduce the action space to clicking links, filling form fields, really basic actions, so that we can highly specialize our language model for slot filling NLU and specialize the NLG to do things like assist you when you have questions about questions. Like, I don't understand, do you want my first and last name? Do you want my phone number with the area code? Questions about questions that are clarifying in the context of task-oriented dialogue, as opposed to, again, just being in the loop with language model, where there is no structured form you're filling out, or there's no structured system that you're engaging with that you need to generate NLG about. The NLG is just about being conversational. So coaching, the idea here is, I call it few shot training with episodic memory. What this really just means is it's a specialized RAG system that retrieves past dialogue episodes with all the context, so the context of all the other software systems. So you can say like, okay, when you're on this form question and you ask someone, do you smoke? If someone says cigars, in this case, we want to track it as yes, right? Or maybe you've experienced a similar situation before that gets retrieved and is surfaced along with other information for the eventual NLG. So this is from our backend. It shows kind of a portion of one of these. Like this is just 2 seconds of a call here, and you can see ASR completes, our VAD completes. There's a large number of LLM calls that are all different specialized things. They're running queries, they're interpreting documents, and then ultimately we're generating, doing NLG and then TTS, and then we're actually playing the TTS while also doing ASR, right? And so there's a flurry of different specialized models that are all working together in parallel to come to some sort of conclusion about what the ultimate NLG should be. And this encourages alignment with the original scripting, and it also encourages the system to be reliable. All right, so that was how we make the system controllable. If the system's not controllable, then you can't deploy it to be a task-oriented system, at scale for businesses. Latency has its own issues, right? Turn-taking, and Jurowski talks about this in the book, is obviously a key issue, turn-taking and endpointing, with trying to build a spoken dialogue system, because in general, if you are hitting 17 external APIs, slowly decoding your LLM, and then slowly generating your TTS, and you take 10, 15 seconds to respond, by second 3, the person is going to ask, are you there? What's going on? And the dialogue state is going to get increasingly out of sync, increasingly into a bad place. You can't solve the very hard problem of turn-taking in a spoken dialogue system with extremely long latency, and you can't feel natural with really long latency. The problem is, like I showed, every single thing in that pipeline adds latency, which means that everything is very latency constrained. So here's another picture of one of our backend systems. There's 2 things for ASR. So we're talking about ASR, TTS, and LLM strategies for reducing latency. I provided references and readings for some of these if you don't know what they are. I'm going to go through it kind of quickly. ASR is the most critical. And there's a couple things you can do. One is if you want, you can do simpler decoding on ASR. If you want to shave some time off, we use beam search, but you can use simpler decoding. The real key one I wanted to emphasize here is, this comes up over and over again. For traditional ASR, for speech recognition, endpointing or figuring out when to trim audio, especially in an online system, is often overlooked. It's own hard problem that has a big impact on the quality of the transcript. Like Andrew mentioned, our first product is Sift, where we analyze literally billions of minutes of speech data a year passively of people talking to each other in call centers. In that case, the goal of endpointing is to cut up into utterances as naturally as possible. In a spoken dialogue system, the goal is to balance trying to make the system very responsive with trying to avoid false positives where you get re-interrupted. It's a lot easier to build the dialogue system to be robust to re-interruptions than it is to build the system to just be extremely fast on endpointing without false positives. And so in general, having specialized models, either neural models or using DSP traditionally, to try to make the bot as responsive as a person. It's hard for a person to know when someone else is done talking. You sometimes get it wrong yourself, I do. And so it's a challenging problem, but very important for reducing latency. For TTS, so you can pipeline it, start moving tokens from your LLM to your TTS, moving frames or samples from your TTS to the phone system as you're continuing to decode from the LLM and the TTS. You can use other optimizations like jitting, bucketing by length for different models, caching TTS outputs. For the most part, a lot of what we say is scripted or repeats, and so there might only be 20, 30% of original NLG in the conversation, and so caching obviously is a big win there. Not using non-autoregressive models, like you guys covered, like VITs and yeah. So like as opposed to like something like Tacotron, where you're autoregressively generating spectrograms, using models that are not autoregressive can have the latency of TTS generation. And then stalling is a really, really useful strategy that people use, which is when you are not ready to talk, or you are not, or you don't think that you're going to be able to complete your thought quick enough, generating ums and uhs and disfluencies is a strategy that I use. I just used it accidentally. And it's actually something that makes the system feel more naturally if done well. And you'll probably hear it when we do a conversation later. LLM decoding, there's a lot of really technical things that you can do to speed up LLM decoding. I kind of bucketed them here and suppressed them. You can look at the references for some of these. Hardware optimization, there's page detention, which it was a paper from last year. Flash attention for managing your use of GPU RAM. Quantization, just in general for model optimization, same goes for model pruning. Again, pipelining, so continuous batching was another paper from the last year. Prefix caching, so if your LLM keeps seeing the same key and value vectors over and over again, you can cache the first couple tokens for the K and V vectors. Parallelizing NLU requests, like I mentioned, like we have a lot of specialized models. If you have a long form, and the person, if you ask someone, if it's like, what's your first, middle, and last name, and you give the person gives their full name, you can do NLU and parse all of that out in parallel. And same with speculative sampling is another paper from the last year and a half, where basically you have a simpler language model, a smaller draft language model, generating a draft, and then you use that as your foundation for decoding. We don't use that strategy. We've tried it, but it does work. It's one challenge with speculative sampling is that as an aside, is that you have to have now two language models, like a bad one and a good one, which is more work. Data preparation, so this is an important one. Like language models generate tokens. The tokens can be whatever you want. They can be system tokens, they can be anything. And so, if you have these highly specialized models, they don't need to necessarily generate language if they're not part of the language generation process, or they can be the data can be aligned to stop sooner, so you need fewer tokens before you get to a stop token. And then obviously model selection, like don't use a smaller model if you can get away with it. It's going to save you compute, it's going to save you latency. All right, naturalness. Naturalness is again often overlooked, like when spoken dialogue systems are designed by committee. A lot of times making the system feel human has traditionally kind of been seen as below the application, especially for task-oriented systems. In general, half of the people that call in the call centers are calling to vent. If the system isn't plastic to that, isn't responding to that, then the system isn't fully implementing its engineering requirements. And so I'm going to talk about just some quick strategies to improve naturalness in these systems. First is TTS data collection. So there's actually a picture of us collecting data. We emulate a call center environment where it's actually going through the phone networks. It's actually using real headsets that's using call centers. We are mimicking the transfer function, the acoustic transfer function of the recording environment, so that it doesn't sound like someone reading an audiobook. So it sounds like someone in with a cheap headset working at a call center. the imperfections and the transfer function, they're meant to emulate reality over clarity, which is counterintuitive, and it's, it has its drawbacks, obviously. But if you have the person that's relatively intelligible otherwise, then you can still get both. You want real conversations, not red text. You want it to be in domain as well as conversational. If you just have the person reading books, it's going to be good at reading books. And not to mention, if you have in-domain scenarios, you're also going to get good TTS coverage for words that matter to you, which, there's going to, if your data set isn't too big, there might be just some triphones that don't show up in your data set, and your model might do a worse job. It's not unusual for us to, if we have a new use case, like, let's say we have a medical triage bot that's used to triage when people call into 911 or urgent care clinics, and someone calls in and they're like, I think I might have diverticulitis, and then she repeats back diverticulitis. If she's never heard any medical words, it's very likely that even if you give her the correct phoneme sequence, that she's not going to put the right emphasis on the word or whatever. And then having an idiosyncratic voice actor and direction, like in general, a lot of times, speech synthesis models just emphasize being right down the middle. Choosing someone that has an idiosyncratic dialect or has some idiosyncratic idioms can make the system, again, feel more natural. NLG alignment, there's a lot of discourse about alignment, so I'm not going to talk about it too much. But in general, a couple things that are very specific to what we do is, one, having a ground truth this is kind of a confusing point, but having a ground truth for your NLG data in your data set for training your language model, so that when you, if you have to do NLG on where are you a human, what's your accent, having a consistent story in your NLG data set makes it so that sequences of NLG are consistent with each other, rather than just being the regression to the mean of a bunch of simulated conversations. It's really the same story as machine learning in general, but it's certainly just TTS, which is the data should be resembling the data generation process that we're trying to model, and that should include the questions that people ask on these calls. If there's a way that if someone asks how you're doing today, or how's the weather, or where are you, ideally it's going to pull from more than just the language model, but you want the data that grounds the language model to be consistent. Otherwise, you're just going to have the NLG is an average over many fake people. And then same goes for alignment on inputs and outputs. So we are trying to build specialized language models that do things like try to manage a call center call well, are able to be aware of the data systems. And so if you align it with those systems, instead of building ChatGPT, you're building a task-oriented system. A couple other small things, back channels, so generating basically acknowledgement sounds, other back channel acknowledgements, control over personality and persona, which I'm going to show when we do the demo. So we provide different controls over personality, which impact TTS, impact the prompting, impact the behavior of the dialogue system itself, and then tracking the emotional state of the bot itself. Right? Again, if you're yelling at the bot should acknowledge that that you're doing that. All right, so the last category is robustness, building something that is actually consumer grade or enterprise grade software, right? So we talked about earlier, we had to deal with noise, we have to deal with distortion, we have to deal with loss. So there's a couple of data augmentation strategies. So ASR systems are not perfect. You guys probably learned that by now. And so, unless you have perfect word error rate, you should augment ASR errors, which can be caused by noise. Someone is calling from their car on speakerphone. You should be able to do that in your data augmentation process for training your language models. So multi-turn spelling errors. So a lot of times people are spelling things in weird ways on these calls. They might be say A as in apple, B as in Bravo. It might be split over 3 utterances. It might get letters wrong. And so you need to, in your data augmentation, emulate these sorts of errors. And then the most important thing is in both your data and in your eventual dialogue system, closing the loop on user errors. So if someone gives you something that it gives you an unusual name, or gives you something that needs to be spelled, like a street name, knowing that you need to verify that and then verify the verification, and that's what people have to do over the phone. It's very tedious. Hallucination management beyond alignment. I already mentioned breadcrumbs, which is just our term for references to why you think that you can say a certain thing before you say it. So again, it's a multi-step process where information is being turned into suggested dialogue and then synthesized into final dialogue. You can do various forms of like chain or tree of thought, which is a prompting strategy, which I'm sure you guys are mostly familiar with. Essentially, in this sort of architecture, you're getting that for free by having large numbers of systems pipelining, generating drafts and references. But you also could explicitly, do something like chain of thought. There's other decoding strategies that are not just greedy decoding that can also be a little bit more resistant to hallucination. Everything from generating special thinking tokens to generating drafts. And then multi-step generation is essentially what we do, where you have system-specific dialogue suggestion and then you synthesize that into final dialogue. One of our use cases is we deploy in hospitals, right? There's hospital systems that call their patients with Gridspace, that get inbounds from patients, we have a use case where one of the largest hospital systems in the U.S. calls every single patient when they get started from the hospital with Grace. If someone just says, "Can I take all my medicine today instead of over the next 2 weeks?" You can't have it hallucinate no or yes, right? Like you can't have it just make something up. Like it has to be referencing something, and so in general, as I think the world gets a little more excited about generative language and speech systems, a lot of times we just get asked for guidance broadly on how to do this, where you're following kind of trust and safety best practices. I think I give this to Andrew for the reading, and he can give. This is a white paper that we have on trust and safety guidelines that we give to companies that ask broadly for our help on this stuff. But there's a lot of things you can do, ranging from traditional reliability engineering to model risk management best practices that go beyond just the engineering stuff I just talked about. I'm not going to read through all this, but I encourage you guys to look at it or talk to me about it after if you're curious. But it's not a small deal, right? Like jumping from having a fun conversation, generating sonnets, to like talking to someone who just got discharged from the hospital who needs to take medication is a very big leap for all four of the engineering reasons we just talked about. And so it's important to start to be mindful of those things beyond just I think the typical discourse around trust and safety, which we use a good conversation about things like bias, but and hallucinations broadly. But once you get into the applied world, there's pretty serious problems that you need to solve. So just returning to the architecture diagram before we do a demo. So again, specialized software systems that are intended to be used by language models as an intermediary to one shared dialogue policy, which is a simple, basically, state machine that is trying to act interactively with someone that's on the phone. That's what we're trying to. That's what we built, and this is what's worked for us. The rewards are great, right? So with even very large embeddings like Roberta embeddings and other pre LLM type embeddings, things like intent recognition, dialogue suggestion, if you can even run those models in a generative mode, was substantially weaker and made the systems less appropriate to be deployed in the real world. So there's big gains to incorporating more and more powerful models into spoken dialogue systems, but the trade-off is for every leap you get in capability, you get 2 steps back in new risks that you have to manage and new engineering problems, just like the laser, right? Cool. So I'm gonna do a demo here. We're going to just kind of quickly build a bot. Like I mentioned in that diagram, right? 3 data systems: one for forms and business process, one for coaching, and one for knowledge retrieval. And then we're going to interact with that system, right? So bring a diagram up. All right, the first thing we're going to look at is the knowledge base here. So normally for large knowledge bases, we'd send out a crawler that would consume all of the documents in your organization for information retrieval. In this case, I've just copied the 224S FAQ. We're building a little 224S bot. And what's going to happen is this is going to be indexed in a traditional information retrieval system that we built. Nothing exotic about the information retrieval really, as opposed to our analytics, which does. And the idea is that the bot is going to be capable of making queries through one language model that just generates queries, and then another model that reviews the top results, right? So it's a pretty typical RAG strategy. So second component is the playbook, right? So here, we'll make this a little bigger like this maybe. So this might look like some sort of dialogue tree. That's not what this is. This is inspired by call center operation systems where you're tracking high-level state of where you are. So like, let's say you have a call center where there's an insurance division and a banking division. Pretty common actually for us. First question I might ask is like, what can I help you with? And some person says like, I need to check my checking account, or I want to get a quote for auto loans or whatever. And right out of the bat, it might split into two separate branches for insurance and for banking, right? And that's kind of the state in the high-level interaction. But within one of those states, there can be a large amount of of behavior. You could build a bot that didn't have a playbook, that didn't have a knowledge base. And you could also build a bot that just had one or two states in the whole playbook. In this case, we built a kind of a toy one where we said, okay, you've reached 224S hotline, my name is Grace, how can I help you? And we have 3 intents. And we literally just named it. So we said late for assignments, course questions, sign up for final project. And then we can just quickly add to this. It's like basically like building a Google form. Again, remember this is going to be rendered like a very simple website with a small action space for, again, another specialized language model that just decides what buttons to click, what form fields to fill, and then gets back scripts from this. So we say, sure, let me help you with that. We ask for your email address. We ask for what topic you want for your final project. Have they done their final projects yet? Andrew? Okay, cool. So this is probably too late for you guys. And then explain what your goal of your project is, and then that'll be submitted, right? And then this goes to a dialogue action that hooks up to our telephony system that figures out whether to route you to a human or do some other downstream action that goes beyond the scope of this. None of what we've done so far is the bot itself. This could be used by people. In fact, the system we originally built for human agents, for live agent assist. This part is the bot, right? So I talked earlier about personas and personality. So we can set the name of the bot, the company, the title, all the stuff goes into the prompting, or in some of these cases, these floating parameters are encoded as vectors or whatever else that impact things like TTS and NLG. A lot of these sliders affect multiple different things, including the dialogue state tracking itself. So we've made her efficient, empathetic, fluid, casual, and verbose. So the last thing is coaching sessions. So this is where we're going to do a simulated dialogue with the dialogue system, and then we're going to correct things. And we can correct NLG, we can correct NLU, we can correct actions taken by the policy. And then that's going to get indexed into another RAG system that can be retrieved to assist with future dialogues. All right, so I've attached a playbook and a knowledge base in this case. So these are the software systems attached to the dialogue system. I'm just going to have it call me.
You've reached the CS224S hotline. My name is Grace. How can I help you today?
Yeah, I know it's getting kind of late, but I wanted to sign up for I think I wanted to sign up for a final project today.
Okay, sure. Let me help you with that. What is your email address?
Yeah, it's scodary@stanford.edu.
What topic are you considering for your final project?
I am considering making a speech synthesis system for dogs.
Explain what the goal of the project is.
I want to be able to use the computer to communicate with my dog.
Mm-hmm. Great. Thanks for your submission. You'll hear back with approval from your tested.
All right. So in this case, we had one NLU failure, but this was just due to an ASR failure. Otherwise, maybe we might want to make the form filling more succinct. And you can see now this is studying this as a few shot example. Let's do one where we have to make it do some NLG, and we're a little tougher on the system.
You've reached the CS224S hotline. My name is Grace. How can I help you today?
Sorry, who is this?
Okay, I'm Grace, a virtual course assistant for Stanford CS224S. How can I assist you? Are you having trouble with assignments, have course questions, or need help signing up for a final project?
Oh, I forgot about my final project. Let's do that.
Mm-hmm. Sure. Let me help you with that. What is your email address?
Sorry, I didn't hear that. What was the question?
Sure. My apologies. Could you please provide your email address?
Do you want my Stanford email or my Gmail?
Either one is fine. Just provide the email address you'd like to use for this project.
Okay, well, in that case, could I use roberts@stanford.edu?
Okay. What topic are you considering for your final project?
Do you have any recommendations? I really haven't been going to lecture or paying attention.
Okay. I'm sorry. I don't for you. However, you mentioned you're considering a topic for your final project. Can you please share what that topic is?
Where is lecture, by the way?
Okay. I apologize for not mentioning earlier, but we have Zoom meetings for each lecture, and they are recorded and posted to Canvas after class. Unfortunately, we cannot release these videos publicly due to Stanford student privacy rules, stating the class will have access to the videos until the end of the quarter. We will not be able to monitor Zoom for questions during class, so we highly encourage in-person lecture participation if possible.
All right, that's not helpful, but anyway, my project is going to be, I'm going to build ASR.
Explain what the goal of the project is.
I think just to complete the project.
Okay, great. Thanks for your...
All right, so now we're going to make some corrections to NLG here. So she pulled something up here, not relevant. We're just going to say Jordan Hall, room 40. We also, by the way, if she took the wrong action, here when she clicked, she did the right action, but we could change what action she took. And then here, I said ASR, and we're going to correct, she didn't know what that was. And again, all this is going into a data set for few-shot prompting later on that's contextualized with the state of each of these software systems that are being served. And typically, for things like question answering, the first line of attack is actually just to improve your knowledge base rather than just copying something from a website like I did and putting the answers in here. But at the very least, you can coach them as well so that they get suggested when those questions come up. But otherwise, here's some of the references, and yeah, ready for questions. Yeah, okay, it's a good question. So the question is, you saw noise tokens getting generated, does it take into account tone? Yeah, so prosody is a big part of spoken communication, how people intonate things and communicate through tone. Our ASR model doesn't just emit transcript tokens, it's also emitting a categorical emotion model output, and so it basically like softmax output, where there's around 20 or 30 emotional states that it's outputting. And then there's a bunch of other stuff that we run in parallel, other specialized submodels like dialogue act detection that are running as well. They're optionally available to the dialogue system. But some of those are mostly used on analytics. Yeah, so the question is like, what would be the drawbacks of just basically having ChatGPT in the loop with like an ASR and like TTS, like API or something from Hugging Face? It's mostly the four things that I talked about, right? So let's if you break them down. From the latency perspective, unspecialized models that are all pipelined in series like that without any optimization for this use case, your latency is probably going to be pretty bad. Now if you use a smaller llama model and you do some, if you're doing the stuff that I talk about in this talk, then you can start to work from there. But if you just naively just pipeline those systems, latency is not going to be great. Control, obviously, all these control systems that I just showed you, all those little software systems I use, the playbook, the knowledge base, these all have specialized models that are designed and trained just for those data systems to interact with the dialogue policy. And so without that, controlling that system, you're going to basically just be jamming a bunch of stuff in the prompts, maybe fine tuning on that, which, there's only so much information you can put into the prompt. And as your prompt is just full of junk, you're also going to get better NLG or worse NLG results as well. And then, robustness, that system is actually obviously going to be very fragile for the reasons I talked about. You're not doing any data augmentation or any specialized training to make the system good at noise rejection. So there's all these problems that come if you do it naively. But honestly, lack of control and long latency are the main two problems that people run into when they start to realize, oh, maybe this actually is a challenging thing.
I thought it was interesting you mentioned the thing about hallucinating answers and how you want to be careful that the model doesn't just say yes, assuming that that
Yeah.
makes sense when it doesn't actually, or could be dangerous for the user? Like, how do you make sure that it knows what things are safe to hallucinate an answer for and what things aren't?
That's a really good question, Ryan. So basically, so it's interesting. So Grace is a 4-year-old product, and when we first deployed, we actually didn't allow it to do any open NLG at all. There were a lot of neural systems, right? There was neural intent recognition and neural slot filling models, but we didn't allow it to do any NLG at all. And as we started to roll out the ability to do freeform NLG, we have customers that are just like, I don't want it to ever say anything that isn't scripted. And you saw one of the personality parameters was verbosity, which puts some limits on when it can and cannot hallucinate. I think we talk actually in that trust and safety document about what we define hallucination as. Because one definition would be anytime a language model is decoding something bespoke and then pushing that off to the caller. I think for us, hallucination is any time when the model is not referencing anything, and so there's no check against it being wrong, whether or not it's wrong. It is basically retrieving the information from the memory of the language model. That's what I would call a hallucination. And so obviously all the things I talked about for hallucination management, like alignment, breadcrumbs, those are all strategies to minimize it. But like there is a gray area where, so like a good example is, very early on when we were, starting to leverage more and more generative models in our stuff, people would ask for help and there would be common knowledge answers that in that special case were wrong. So like for instance, we had an insurance use case we were presenting to a very large like car insurance company. And it asked for like your member number on your like member card. And you could ask like, like where do I find my member number? And it's just common knowledge on the internet, in our data set, use a trained language model. But for that company, the fact that it retrieved just happened to not be right. Same goes for like something like if you talk to like if you're doing credit card authorization, someone's calling in just wants to activate a credit card, very simple bot use case. And you might say like how many digits is the number on the back, or how many digits is the credit card number? For the most part, it's like 16 and 3. But if it's like American Express, it's actually a different number of numbers, right? And so it might decode something that's mostly correct most of the time. It's a hallucination all the times because it's not referencing anything. And so by having upstream systems that have to retrieve that information and otherwise say I don't know because I couldn't find it, you've split the problem in the subtasks, and that puts some pretty serious guardrails on it. Yeah, so again, a really good question. So the question is basically for like something like GPT-O or some sort of multimodal model where, it's still to be seen whether there's actually speech synthesis in GPT-O, but there definitely is ASR. So multimodal models, the main advantage, to be clear, there's no ambiguity at all that within a few years that eventually building spoken dialog systems will be done with more monolithic multimodal models. Like there's no reason for that not to eventually be the endpoint. The upsides are fairly minute. So the biggest win is architectural. So if you have ASR and if you just have ASR and the language model are the same graph, so imagine like you can't quite hear someone, having things like ASR uncertainty get passed along to the language model would allow it to be more likely to generate something like, sorry, it was really noisy, could you say that again, without needing to decode like a noise token and then have some sort of reaction to that. But for the most part, the gains that we've seen for using a multimodal model in these task-oriented use cases are pretty low. The other thing is like, notice we were using lots of specialized, intentionally small models. So either you train like 8 multimodal models that all consume audio, or you still have a large number of non-multimodal models, and so. But I think eventually starting to align big multimodal models with control systems and stuff is probably where things will go. Yeah, so I think in general, there's this trade-off between specialization and not repeating work. As you start to build models on giant corpuses or on data sets that are kind of inaccessible, there's a lot of benefit to starting with a foundation model. and that's not new, right? Like, using bird embeddings or word-of-vec, like using, models that someone else trained and then fine-tuning or working from there is a good idea, I think that one challenge that we've seen over the years when you start getting into the speech world is that Public ASR data sets are small and very far out of domain. Same goes with speech synthesis. And speech synthesis, you might be targeting a specific voice. Even if you train a multi-speaker model with speaker embeddings and are able to few shot mimic them, that's still going to vastly underperform a model trained on a large data set from that speaker. And so foundation models for the more audio side of things, the lift so far is probably not as big just because the data diverges more from reality. But when you're just you want to train the system to on a very large text corpus to know about egg recipes and everything else under the sun, it's hard for everybody to do that. And so if you don't have that as a starting point and you need to do freeform NLG, that's very humanistic, that's a good starting point.
If people have to run for other classes, please feel free. Anthony, Gridspace, thank you again.
Yeah, thanks guys.
Hello, thank you for calling Gridspace's YouTube channel. Did you make sure they liked the video and smashed that subscribe button?
Yes, I did.
And ask them to leave any questions or thoughts in the comments. It helps me a ton. Thank you for watching, and if you'd like to talk to me yourself, go to gridspace.com and click on any one of our demos. Thank you, and talk to you soon.
Thank you, Grace.